Okay, homework 6, problem 1. We have a 200 turn coil. It's 30 centimeters in diameter. It's operating at a radio frequency of 100 megahertz. The incoming electromagnetic wave is perpendicular to the coil and has maximum strength of 1 times 10 to the minus 12 Tesla. So what power is incident on the coil? Well, we can work this from a couple of ways, but first, the question is what power is incident on the coil. And so if we look for power in all of this, and the power is in the equation, the intensity is the power divided by the area, right? So power is simply intensity times area. Well, we also have, right, that the intensity is from our equation sheet, we pop over there, 1/2 CB squared over mu naught, right? So 1/2 C B squared over mu naught, right? Looks a little goofy, but we'll leave it as is. So this is the intensity. And we know everything in this because we know C, we know mu naught, and we know the B field. All right, so we have B is 1 times 10 to the minus 12 Tesla. We have C is 3 times 10 to the 8th, 10 to the 8th meters per second. Right, and we have mu naught equals 4 pi times 10 to the, gotta find mu naught real quick. Okay, so mu naught is 4 pi times 10 to the minus 7th Tesla meters per amp. Right, so 10 to the minus 7th Tesla meters per amp. Okay, so that's all of our constants, are all the things we do know, and so we calculate intensity, right? Pop over to Excel. All right, the B field, 1e minus 12, speed of light 1e8, magnetic permeability of free space mu naught, 4 times pi times 1e minus 7, right? And so the intensity is 1/2 times C times B squared divided by mu naught. So we got 1.19 times 10 to the minus 10th watts per square meter. All right? So the intensity is 1.19 times 10 to the minus 10th watts per square minus 10 watts per square meter. That's the intensity. All right. Now we need to get the power. So the area is pi r squared, right? So that is pi times, what's our diameter? 30 centimeters, so 0.15 meters squared, right? So pi times 0.15 is our area. Pi times 0.15 squared, so 0.071 0.071 square meters. All right, and now we're down to our power is intensity times area. All right, our intensity times our area is 8.4 times 10 to the minus 12 watts. Right? 8.4 times 10 to the minus 12 watts. And that's the answer to part A. Part B, what is the average EMF that's induced in the coil over 1/4 of a cycle? Okay. Let me put up. So for part B, you have to remember that your EMF is minus your change in flux with the change in time. Right? EMF is minus the change in flux over time. And the flux is just the B field times the area times the cosine of the angle, right, that the B field makes with the area. But in this case, oops, the angle we're given is perpendicular, or 0, right? The angle between the perpendicular of the surface and the B field is 0. So this is just the flux equals the B field times the area, right? So we know the B field, we know the area, so the flux is the B field times the area. Is 8.44 times 10 to the minus 12th. Tesla meter squared, right? That's the flux. That's the peak flux, right? And in 1/4 of a cycle, if you remember correctly, when you look at a cycle, right? When you look at a cycle, it goes up, it starts up and down, right? In 1/4 of a cycle, you go from the peak down to 0. All right, so that tells us that delta phi b, right, we're going to go from this maximum that we have here of 8.44 times 10 to the minus 12 Tesla meter squared down to 0. So delta phi b is 0 minus this. So this tells us the delta phi b we're after is just minus 8.44. All right? Okay, so that's delta phi b. One quarter of a cycle, right? If we think about what that means. So when we've got a cycle, this is a sine wave or a cosine wave, right? The length of one cycle is the period t, which is 1 over the frequency. And we have the frequency, right? So we have that the period equals 1 over the frequency equals 1 over 100 times 100. It's megahertz, so times 10 to the minus 6. And the units on this are going to be seconds, right? So that's 100 times 10, that's 1 times 10 to the minus 8. Nope, not minus 6. Mega is plus 6. Sorry about that. 6, right? Altogether, this adds up to 10 to the minus 8th. So 10 to the minus 8 seconds. 10 to the minus 8th seconds is one period. What we need is a quarter of a cycle, right? And so that's just 0.25 delta, think you'll be able to spell delta now. Delta T is just 0.25 times 10 to the minus 8th seconds. All right, putting it all together, EMF is minus delta phi B over delta T. So delta phi B is minus 8.44. So it's going to be plus that. Let's take a look. We have 8.44 times 10 to the minus 12th. And we have 0.25 times 10 to the minus 8th. Right? And so delta phi B is the flux divided by the time. And so 3.38 times 10 to the minus 3. 3.38 10 to the minus 3 volts, right, is 3.38 millivolts. And that's it for part B. Okie doke. Okay, on to part C. The radio receiver has an inductance of 2.5 microhenries. What capacitance must it have to resonate at 100 megahertz? All right, so part C, we're being asked to create a resonance frequency, all right, which, if you look at the formula sheet, it's just given by 1 over the square root of LC. All right. Now we have the inductance is 2.5 microhenries. We have the resonant frequency is 1 times 10 to the 8th hertz. So we just need to solve this, right? Need to solve this for capacitance. So square both sides. It's going to give us F naught squared equals 1 over LC, right? Now we're going to multiply both sides by C, and we're going to multiply both sides by 1 over F naught to get to C. The capacitance is 1 over L F naught squared. All right, and that's going to be, we have 1e to the 8th is our frequency. We have our 2.5 microfarads. So 2.5 e minus 6 farads. Farads? No, henries. Sorry. Microhenries. Okay. And the question is, what then is the capacitance? Well, the capacitance is 1 divided by the inductance divided by the frequency squared is 4 times 10 to the minus 11th. Or 40 times 10 to the minus 12 coulomb farads equals 40 picofarads. And that's it for problem 1.